Alright, continuing. We take a break from talking about the matrix of a transformation momentarily, develop a little bit more terminology about maps. And so this should be a review, but you may or may not remember it. I don't know if you've had this in a previous course or not, but here it is. So if f is a function from a to b, and you have some subset of a, the domain, then you can talk about the restriction of f to a1. It's denoted f bar a1, and that's a new function with the domain being scaled back to a1. The codomain stays the same, and it's simply defined by the value of the restriction is equal to the value of the function. It's just that the inputs are limited to the subset a. So that's a restriction of f to a1. In the same sense, if you have g as a function from a to b, and again, some subset of the domain of g such that g restricted to a1 is f, then we say that g is an extension of f to a. So if you think about it for a second, it's fairly obvious that given a function, given a subset of the domain, the restriction is unique, right? But on the other hand, if you think about extension, right? So, just think about a and b both being the real numbers, or some subset of the reals appropriately. So, if you start out with, say this is the graph, right? Say that's, excuse me, that's y equals to f of x, for x in, I don't know, 2 to 3, right? If we start with that, and then we ask, okay, so what are possible extensions of that function? Well, I mean, the possibilities are pretty much limitless here, right? I mean, you could do like this, right? Or you could do, like that. I mean, you could, but just as well you could do, I mean, I don't even begin to have enough colors to illustrate the possibilities. You could make it jump. I mean, maybe it's not a continuous extension, maybe it's a discontinuous extension, I mean, there's so many different ways you could go past what's given in green and look at these extensions to the, if we kept going to the whole reals, right? So certainly for a generic function, the idea of extension is far from unique. So extension is far from unique for a generic function, but we do have a pretty nice theorem for linear transformations. Theorem. If t is an element of the linear transformations from v to w, right? And if v1 is a subspace of v, then t restricted to v1, which again would be a linear, this is the theorem. In fact, this restriction is in the linear transformations from v1 to w. So if you take a linear transformation and you restrict it, you get a linear map again. That's kind of nice. But the other more impressive theorem has to do with extension. So here's the extension theorem that's interesting. If we have, and I have two statements of it. First, if beta is a basis for v, and suppose v1 through vn are in the basis, then specifying, if we say, okay, like t of v1 is w1, t of vn is wn, so if we pick out these w1 through wn's for some a bunch of vectors in w, then that uniquely defines a linear transformation t from v to w. Let me state it in terms of restriction as an extensions again here. Let's try this again. So in the purple, if we have s going from beta to w, again, beta is the basis I just talked about, given by s of vi equal to wi and w, for I equals 1 to n, then there exists a unique, that's what this means, there exists a unique t going from v to w, such that t restricted to beta is s. And I still haven't mentioned, and to be more clear, that's not enough. I really should say, what other special thing do I know about this? Not just any old t. I'm assuming there exists a unique t in the linear transformations from v to w, which matches the given data. In other words, there's a unique linear extension from s to t, okay? I can say this in abstract mapping terminology, but here's how you actually do it. So suppose you know the values of t of vi. Here's how you can build t from it. You know, t of the sum, assuming linearity. This is extending linearly, basically, is forcing linearity in the map. The thing is, if you use this to define the linear extension of t t off the values of the basis, then you can prove that that's in fact a linear map. Anyway, that's one of your homeworks. We'll talk more about that tomorrow if you want. Here's some specific, tomorrow being Thursday, or possibly Friday, depending when you watch this, I suppose. Or who knows? Anyway, so anyway, here's an example. If we look at the vector space being possibly degenerate quadratic, quadratic polynomials, let's say, and if I say t of 1 is t plus t squared, I say t of t is 3t plus 2, and t of t squared is 1. All I've done is I've told you what the values of t are on the basis, 1t squared. But that uniquely defines what t can be if t is to be a linear map. See, because if t is linear, that means that t of a plus bt plus ct squared is this, which is that. So that's it. That's it. Another important example. Let me get this example. I keep coming back to this by accident. There we go. Get out of the way. Another example. We could define the coordinate map. All right. So actually, let's just say this map phi sub beta for the moment. Suppose phi sub beta of 1 is e1. Phi sub beta of x is e2. Phi sub beta of x squared is e3, like so. All right. So I've uniquely defined this phi sub beta on the set beta, which by the way is the basis. Right, this is basis for what? P2, right? Or if you like, R adjoin x, well, polynomials in x with degree n less than or equal to 2. Anyway, so that's the basis. We've specified phi beta on the basis. That uniquely fixes the action of phi beta as a linear map. According to this calculation right here, we get ABC. Of course, you recognize that this is, of course, the coordinate map, a plus bx plus cx squared, right? So beta. So there you go. That's the principal use of this extension theorem that I'm bringing up, which is just this definition. So phi beta going from, say, v to fn, where v is equal to the span with respect to the f of beta for basis beta, let's say v1, v2, vn, is uniquely specified, defined by phi beta of vi equal to dj. I'm sorry, I'm kind of mixing a theorem into definition at the moment. My bad. But the point is, if you say that this phi beta map maps the jth abstract basis to the jth standard basis for your vector space V by the theorem, the unique linear extension theorem that I just mentioned and sketched part of the proof of, that will uniquely define a linear map phi beta on all of the vector space. And by the way, moreover, it's something we've already talked about. In fact, phi beta of, say, a vector x is nothing more than the coordinate vector of x with respect to beta. Okay, so this is the coordinate map. The coordinate map is important. Just to emphasize some of its maps, some of its properties rather. Phi beta, again, is a mapping from V to, where here n is the dimension of V. What can I say about phi beta? Well, phi beta is a bijection, which is linear. In fact, it's an isomorphism from V to Fn. Okay, and we'll be using it a lot in what follows. Okay, so that's my 2 cents here on linear extension and restriction. And so we'll come back again here in a minute or two, and I will give you a short tour of how we calculate the matrix for a linear transformation with respect to possibly a non-standard basis.